Hey guys, what's the crack? Hi Mina. Hi Emma. Hi team Sarah? Sire? What does the SIAR mean? Hi Relax and Rain. How's y'all summer? Are you American? Do you have American family? Y'all, I haven't heard y'all in a minute. Summer's coming to end though for you guys, isn't it? You're back at school, what, in 2 weeks? Is it even 2 weeks? Probably a week and a half, isn't it? What date is it? 22nd? Yeah, it's like a week and a half, right? Can we hear me okay? Anyone there? Hi, Ishak. So we can hear me good. Oh, grand. Hey Omar, how you doing? So we'll start in like a minute maybe. So yeah, is it week and a half you're back? Are you back September 1st, eh? Hey JMB. Hello. Don't like the itches. Back in the 6th? Oh, that's nice. So you have like a bit of extra time, eh? Yeah. It's so different. I couldn't imagine going back to work in a couple of weeks. That's mad. I know I'm like actually full-time working now, but it just seems so different from being in the classroom, you know? Plus it's kind of nice wearing a t-shirt to work rather than have to wear, I don't know about your teachers at your school, but we had a rule where I had to wear blazers every day. Your UCAS stuff. Aye, right, because you need to finish. I'm surprised you didn't start it. I thought you didn't apply to UCAS until normally September, October, right? Or I guess if you're applying to Oxbridge, you got to apply quite a bit earlier, don't you? Blazers Daily is mad. I 100% agree with you. Like literally, I had to invest so at some schools the teachers wear like a blazer every night on like parent stage. No, the school I just came from, they just wear one every day. So you know how like teachers tell you off for your uniform. If I came out of my classroom without my blazer on, I'd get sent back to go put my blazer on. Like it's mad. Hi Ethan. Okay, so we're going to today we're going to do nuclear physics. So if you can see that right. So we're doing nuclear physics. So this topic, again, like every school, every teacher teaches things at like slightly different times, right? So nuclear physics is actually the one that I always teach last. So if you're in my school, or if I was your teacher, I'd probably end up teaching it to you right at the end. So we're talking like maybe like March time. But again, like sometimes you have two physics teachers, so they have the curriculums, you get taught at different times. So we're just going to start first with a bit of GCSE knowledge because you've not done nuclear physics since then. So just the first one is, what's the three main types of radiation that you learned in GCSE? What do we also know them as? Like what's their like other name? What's their range in air and what can they stop by? So just pop in the chat. Yeah, Kai, hello, beautiful. Alpha, beta, gamma, nice. So alpha, beta, gamma. Hopefully we're okay with how to draw them. So like normally it's the Greek letters. Yeah, Ethan, beautiful. Emma, beautiful. Omar, lovely. So what's their other names for alpha, beta, and gamma? Ethan, hammer. So what's their other names? So like an alpha particle is also known as a something. A beta particle is also known as a something. Beta, I'll give you a hint, it was like a fast moving. Kai, beautiful, right? It has to be a helium nucleus. Why do you have to say nucleus? So you don't get marked for helium. Helium nucleus, beautiful. Yeah, team SIAR. Yeah, good job. It's going to be a fast moving electron. Fast moving electron. Nice. Yeah, good job. There's no shells of electrons. Nice. So an alpha particle is just the nucleus. Okay, so if you remember some of your chemistry, remember we just draw an atom. Inside the nucleus, you got your protons and your neutrons. And then around the atom, you had your electrons orbiting. That's what you did in GCSE. So that's why atoms, we always said we're like electrically neutral. So helium on your periodic table is 4,2. So that means I've got 2 protons, I've got 2 neutrons, and then because it was an atom electrically neutral, I had 2 electrons. okay? But an alpha particle, like we just said, isn't the helium atom, it's the helium nucleus. So we only have the 2 protons and 2 neutrons, which tells us then its charge must be +2, or its relative charge is +2, right? Yeah, so exactly what JMB said there. So that's what you're going to put in your year 12 physics, right? Year 12 physics, your A-level exams. You're going to write helium nucleus, and then you're always going to say it's got 2 protons and it's got 2 neutrons inside it. So you say both things, okay? And then gamma, like everyone just said there, it's going to be an EM wave, which is nice. Yeah, it's an EM wave, an electromagnetic wave, or it's radiation. Okay, do you remember their range in air and what they're stopped by from your GCSEs? What was their range in air and what are they stopped by? So, alpha particles, hopefully you know, have got really short range, right? Because we use them in our smoke alarms. Yeah, it's really small range, yeah, because they can be stopped by a piece of paper. Good job. So alpha particles can't get through paper. So like if I had an alpha particle in my hand, well, you're not in front of me, but let's say LaJoy, the chemistry teacher, was here and she was in the room with me and I had an alpha particle in my hand. If I put a piece of paper between me and LaJoy, she wouldn't get harmed by the radiation, right? Because the paper completely absorbs all the alpha particles because they have such a short range. And the range in air is roughly around 5 centimeters, right? So roughly around 5 centimeters is the range. Yeah, beta is your next one. It's stopped by aluminium. So aluminium, remember, is like, you know, when you're cooking like your chicken nuggets or whatever on the oven, the aluminium foil, that sheet of foil. So let's say I had a beta particle in my hand, I could put that aluminium foil between me and LaJoy and she won't get sick, right? Because the aluminium will completely absorb all the beta particles because their range in air is around 1 meter. And then gamma. Yeah, good job. So gamma can actually never be completely stopped. We can reduce it by using roughly 5 meter thick lead or concrete. So like imagine a whole room filled with lead or concrete. You can significantly reduce it, but technically you can never stop it. And its range is infinite in air. Okay, so infinite in air. Okay, so these things you do need to know because it won't ask you a question like what is the range of beta in air. You'll see some examples today. It'll give you some information and you're just supposed to remember that beta has roughly a range of 1 meter in air. So when you see the examples, you can apply it. Okay, so what is ionization and which type of radiation is the most ionizing? So what is ionization and which type of radiation is the most ionizing? And then question 3 is a bit of math, so you can figure out. So ionization, I have seen this come up in 1 markers. Hopefully you get your test questions something like this for a 1 marker. Yeah, good job. Alpha particles are the most ionizing. So what we've written them here, alpha is like the alpha male is like the strongest male. But you're not going to write strongest in your test, right? So alpha is the strongest male, so it's the most ionizing. Then beta, then gamma. So we've written them in order of their ionization. And then so ionization, what it means is that you can either knock electrons off or you can add electrons, right? So ionization, be careful. The word ionization actually means the gain or the loss in electrons. Okay, so it's the gain or the loss in electrons. And you won't get marks in your AQA paper if you write ionization is the loss of electrons, okay? Because they didn't tell you that it's been ionized and became a positive ion. They just told you ionization. Just be careful in your paper. You can't ever write ionization is the loss of electrons. You got to write it's gain or loss of electrons. And they actually do put that in bold if you see it in some past papers. Okay, so we know alpha is the most ionizing, makes sense the most ionizing because it's charged, like we just said earlier, it's got 2 protons, its charge is +2, whereas a beta particle is a fast-moving electron, so its relative charge is -1. So alpha is the most ionizing because it's the greatest ionization, right? Yeah, ions can be positive, negative, JB, yeah, perfect. Okay, so this one, I just want to see if you can do a bit of math to get started into the math mindset. So let's say both alpha and beta, they lose 5 times 10 to the power of -18 joules of energy every time they collide with air. So every time they hit an air molecule, they're going to lose that much energy. Let's say every alpha particle can make 10 to the power of 5 collisions in a centimeter, and a beta particle can make 10 to the power of 3 collisions every centimeter. What is the range of both of them if they both start with 4.8 times 10 to the -13 joules? So what's their range? Put in the chat. So what's their range? So we're starting with this much energy, and then every time they collide, they lose this much energy. So you'll do something first, and then you know that alpha particle, every centimeter has 10 to the power 5 collisions, so how many centimeters can actually travel? And beta particles have 10 to the power 3 collisions every centimeter, so how many centimeters can it actually travel? So hopefully the first step we're thinking here is, if that's the energy I start with, and every collision loses this much energy, the first thing you need to figure out is how many collisions are going to happen. So that's the first step, figure out how many collisions there are. And then when you know how many collisions there are, if alpha does 10 to the power 5 collisions in a centimeter, figure out how many centimeters that can travel if now you know how many collisions there are. Anyone want to give us a first guess? So when you divide the two numbers, hopefully you can see that what's going to happen in total is 96 thousand collisions. That's why I got it. So we do 4 times the power of 8, 4.8 times the negative 13, divided by 5 times 10 to the negative 18. That's how many collisions are going to occur. And if air can have, every centimeter, it has 10 to the power 5 collisions. So that's how many collisions can occur. In every centimeter, there's 10 to the power 5 collisions. All we need to do, yeah, Emma, good job, brilliant. So you just divide the numbers. So you do 96,000, divide it by 10 to the power 5 to figure out how many centimeters that alpha can travel. And you hopefully get 0.96 centimeters, like Emma did, perfect. And now I want to figure out how many centimeters the beta can go. So again, it can do 96,000 collisions, divide it by 10 to the power 3, and hopefully you got 96 centimeters. So that's what I'm trying to show you there is, yeah, Omar, thank you, 96 centimeters. So what you just showed me there is roughly the range of beta is about 1 meter, and here alpha is about 1 centimeter, okay? But roughly we want to learn about 5 centimeters, okay? So it's just get you in the mood of using your calculators and use a bit of math, okay? Okay, so you probably know what this did. Did it give me a yes or no if you heard about him in the news? So he was a Russian spy, and then he was in the UK, and he was killed by radiation poisoning. Did you hear about him? So it was quite a while ago now. Yeah, it was 2006. So what happened was his tea was contaminated. So what they did was they dropped radiation into his cup of tea, right? So contamination, what it means is the unwanted presence of radioactive atoms in other materials, right? So his tea wasn't radioactive. That doesn't make any sense, right? But someone they contaminated his tea, and it was the unwanted presence of that radiation in his tea. So what radiation can do then, it can damage your living cells. It can, if it happens in certain cells, you can get mutations. And if it happens in your sperm cells, your egg cells, that can be passed on to your future generations. Okay, so the key thing here is just making sure you know that radiation can kill you. And what radiation do you think it was? So we put it in his tea and he died. Do you think it was alpha, beta, or gamma? So alpha, beta, or gamma? Yeah, good on you, right? So it had to be alpha radiation because it's the most ionizing, right? So alpha radiation, that's why, think about the man who tried to kill him. The man can carry alpha radiation in like a little plastic bag, right? Because alpha can't even get through paper. So if the man who was trying to kill him just kept the alpha particles in a little paper bag, he would never get sick, right? I can hold alpha particles in a paper bag because alpha can't get out paper. And when he put it in his tea, again, he was fine because alpha would be able to get through that cup. But because your man drank it and the alpha particles went inside his body, he ingested it, those alpha particles are inside my body now. And then because they're so ionizing, they'll ionize, they'll kill my cells, they'll change the DNA of my cells. That's how you can get cancer. And if it happens to a sperm or egg cell, then it gets passed on to your future generations. Do some samples emit more of a certain type of radiation than other? Yeah, so when you look at different atoms emit certain types of radiation based on what they look like. So what we're going to look at is some types of atoms, they just have too many nucleons, right? They're too large, like uranium-235 is really large. So it's always going to probably emit an alpha particle because it wants to become smaller. Other types of radiation, they just might have too many neutrons in them, so they'll do a certain type of radiation. And some neutrons have too many protons in them, So nucleuses have too many protons, they do a certain type of radiation. So we're going to look at that today, figuring out what type of radiation will come off. Yeah, so it's based on how many, if they're too proton heavy, if they're too neutron heavy, or maybe they're just heavy to begin with. Yeah. Okay, so just a quick recap before I move on. So we just said say we have a uranium-238 nucleus, but uranium-235 is the one that is enriched. So that's the one that they use in nuclear power stations. And a cool fact, I didn't know this, but the government, so you know how there's MI5 and MI6, and I don't know what you call the ones in America, the FBI, they actually monitor how much uranium-235 different countries import and export. Because uranium-235, the only two reasons you really want it is because either you're building a nuclear power station or you're building nuclear weapons. So uranium-235 is something that countries really monitor how much other countries are importing or exporting it. So uranium-235, I thought that was cool. Uranium-235 is the one that's the radioactive one. Uranium-238 is also radioactive, but it's not as good as uranium-235. So remember the three types of radiation, we're saying the main ones are alpha, beta, and gamma, but another thing is neutrons, okay? So the one that's a bit new is neutrons, right? So remember alpha, we just said earlier, is a helium nucleus plus 2 charge. You have to learn these numbers. You had to learn them in GCSE, so just make sure you recap them. Helium nucleus, 4-2. Gamma, we said was an EM wave, 0 mass, 0 charge, right? It's just a beam of high energy. And then beta particles, you learned that a beta particle is a -1, right? You learned it's a fast moving electron. So because it's an electron, we say electrons, their mass is basically 0, and then their charge is -1. So that's why, remember the bottom number is the proton number. This charge here, that's +2, 2 protons. So that's why I write -1, because its charge is -1, okay? And there's one more to know about, is beta positive, okay? So this one is beta negative. Okay, so beta negative is a fast moving electron, and then beta positive is a fast moving positron, right? Yeah, Kai, positrons. Have you guys learned anything about antimatter yet? Because we're going to cover, can't speak, we're going to cover a little bit of that today. Oh, we have, right, okay. So what a positron is, it's called an antiparticle. So your electron is like your real particle, and your positron is your antiparticle. So antiparticles, you know, have the exact same mass, they just have opposite charges. Okay, so they have opposite charges. So exact same mass, opposite charges. Is antimatter, now you're making me confused, that's paper 1 or paper 2. Particle physics is paper, oh, I can't remember. Particle physics paper 1, isn't it? Yeah, so you would have done it, yeah. So an electron, yeah, thank you. That's how mind blank. Yeah, so particle physics paper 1. Yeah, it's paper 1. You do. Oh, now you're making me doubt. Wait, now we have to recap the topics. Paper 1 is mechanics, waves, electricity. Yeah, particles. Yes. Okay, so positrons have the exact same mass, just opposite charge. Yeah, you would have done it ages ago. Yeah, you're right. Exact same mass, opposite charge. So it's a positron. So again, what we're looking at is alpha decay is our radiation. We're going to beta decay, beta minus decay, beta positive decay, and your alpha particles. Okay, again, you have to know these numbers roughly. So alpha, we just said, can't get through paper. It's completely absorbed. So just remember the word absorbed is the one they want you to use in their paper. Completely absorbed by paper. Beta radiation is completely absorbed by aluminium. But gamma radiation can get through aluminium, it can get paper, and it is reduced by the lead. But it has to be really thick lead or really thick concrete. Okay, so Geiger tubes is what we use to measure background radiation, and you've probably learned about these again in your GCSEs. And if you've ever watched Ghostbusters, so Ghostbusters, the premise of the movie is that they think that ghosts are radioactive, so they emit radiation. So then, you know, Ghostbusters, they have that little like toy gun thing they carry around. It's a Geiger tube, and then when they find the clicking one, yeah, JB. When they find the ghosts, so it'll go like beep, 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 beep. And so when it goes beep, 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 they know that there's a ghost there. So that Geiger tube is what they use in Ghostbusters. So a Geiger tube is just how we detect radiation, okay? So there's loads of background radiation all around you, right? Radiation's going through you all the time. So we know it comes from the ground because where our uranium rocks are, right? We dig it up to get uranium-238, and we dig up the ground to find uranium-235. There's also radiation in your food and drink. We know that there's radiation coming out of the sun. From nuclear weapons testing, there's loads of background radiation. Nuclear power, there's loads of background radiation. From medicine use of it, there's loads of background radiation. Okay, so you can clearly see that man-made is roughly about 13%, but naturally there is loads of radiation that we're exposed to. So that's why when we do practicals in this, so you will do a practical in this, the first thing you always have to do is you have to take all radiation out of your room. So there's your room. You remove all radiation from the room and you leave the Geiger counter in the room for like as long as possible, right? So maybe a couple of hours, and you figure out what that background radiation is inside the room, right? Because you want to figure out that you're not starting with zero radiation. So then if I want to figure out the difference between alpha and beta, what would I do? So let's say now I'm in my room, I have some atom, some unknown atom, and I don't know if it's emitting alpha or if it's emitting beta. And here's my Geiger tube. What would I do to figure out if this atom is emitting alpha or beta? So I've already done my background check. I've already figured out how many counts are in the room already, just for background. And then I've got some unknown atom, some unknown nucleus, say nucleus, and it's either emitting alpha or beta. Put some paper in the tube. Yeah, so you put some paper. So this is my Geiger tube. So we're gonna put some paper in front of it actually, Emma. So yeah, thank you. So what we can do is we've got alpha and beta. I know that alpha can get free paper. So what I'm going to do is I'm going to have my Geiger tube and I'm going to put a piece of paper between the source, my nucleus, and my Geiger tube. And if it still picks up numbers, so if I still get a count rate, so remember I do have numbers anyway from the background, but if the count rate goes up higher than the background count rate, I know there must be beta coming off that nucleus because it's able to get through the paper. But if the number on the Geiger tube just stays at that background count rate, then I know it must have been alpha because whatever it was can get through the paper, right? So then same thing, next question, how would we know the difference between beta and gamma? So again, some unknown nucleus. I've got my Geiger tube here, and I don't know if it's emitting beta or if it's emitting gamma. So what would you do? Yeah, thank you. Yeah, Kai, beautiful. Right, what we're going to do here is I'm going to put a sheet of aluminium there, right? Probably like quite thick aluminium, just to make sure we're good. So I've got my Geiger tube. I've got my background count rate. Let's say it's 300 counts, okay? So let's say my count rate says 300. If the count rate doesn't change, I know it must have been beta because it's not able to get through the aluminium. But if the count rate goes up, let's say it goes up to 900, that means I know there must have been gamma because it's able to get through the aluminium and get into my Geiger tube, okay? Okay, other questions that come up. So we're talking about paper free here now. We're talking about the practical paper. Why do you think the number on the Geiger tube isn't always accurate or isn't always correct? So why do you think the number on the Geiger tube isn't always accurate or correct? Okay, so these are like common questions. It's basically like when you do this practical, what do you need to consider? So let's say again, I've got some unknown nucleus and I want to know what its decay rate is. I want to know what it's, right? Good job, right? So the first thing is there is background radiation, right? That's the first thing. That's why my number's always off. So the first thing I need to do in the room is I need to count what the background radiation is with no radiation in the room. I need to make sure there's nothing in that room. And let's say the background count rate is 300. And then when I bring my radiation in the room and the count rate maybe goes to 900, I know that the corrected, so it's called the corrected count rate. The corrected count rate is actually 600 is what came from my source, okay? So again, we have the source completely out of the room and we measure the background count rate. Then I bring the source in the room and now it goes up to 900. So I know the source itself gave me 600 and that's called the corrected count rate, okay? Why else could it be wrong? So let's say I do this experiment. Why else might I not get the real decay rate of this atom? Why would my count rate might be off? What do you know about decay? So I've got my Geiger tube, I'm trying to record the radiation coming off this unknown nucleus. Yeah, JMB, good job, it's random, okay? That's a big one that you have to make sure you mention in paper free. It is random, okay? So what that means is we can calculate a probability that this nucleus will decay. But again, it's not an exact number. So for example, the probability that I flip a coin and get a heads is a half, okay? But I could flip the coin 8 times and always get tails, okay? Because it's a probability that I should get half heads, but it's not, I can't ensure that it'll always be half heads, half tails. So same with radioactive decay, it is random. We can have a probability of decay, but again, it could be, say we're recording for a minute, this might never decay. So I might get a number of just 0. Well, it won't be 0. Let's say my background's 300. So my background's 300. Let's say in a minute, nothing gets decayed, so it says 300. But it might be a minute and loads decay, and it might go up to 1,000, right? So because it's random, that's why our numbers won't always be exactly what we need them to be. Okay, so the first fact is we know there's some background radiation present. Second fact is it's random decay. And then the third one is that you have to think about we don't know what radiation's coming off, right? So we don't know what radiation's coming off. Why, if it's alpha, could there be a problem? So we don't know what radiation's coming off. If it's gamma, we're probably fine. If it's beta, we're probably fine. Why, if it's alpha, might I not get an accurate result? So I have my nucleus in my room on my desk, and I have my Geiger tube on my desk. Yeah, Emma, good job, but what would you write in a test? So it might not reach why. So remember, you got to tell them you're paper free. We're trying to think what's the reasons. Yeah, it does have a short range. Good job, because so where does it go? So I'm asking you kind of. So alpha has a really short range. So like what it having a short range means that where did it go? Yeah, so I'd write in my test, it could be alpha being emitted. Alpha has a really short range, so it might not reach the Geiger tube. It might not reach the Geiger tube because it could be absorbed by the air particles in the room, right? Okay, so again, we're telling them the problem. So just paper free is like a little tiny different bit of thinking, right? Paper free is we're thinking, what's the problems and why do those problems happen? So the problem is that when I do this result, I might not get accurate readings because it's random. I might not get accurate readings because I need to remember there's a background count rate, so I need to take that background count rate first. Other problem is, what if it's alpha that's being emitted by this nucleus? I know alpha is really short range, so it might get absorbed by all the air particles in my room before it reaches my Geiger counter. And a nice way that one of you mentioned there, I saw it, but I missed it now. Someone wrote about a vacuum. So yeah, Team Sarah, something you could do to improve this then is we probably could do the experiment in a vacuum, right? Okay, the last one then you need to know about is called dead time, okay? So this is probably new to everybody. So dead time is the problem with Geiger tubes and why your readings might always be right. So I'm just gonna write it here. So it's called dead time. So another reason why your readings might not be accurate is because of dead time. So what happens in your Geiger tube? In your Geiger tube, we have a gas, okay? So let's say my alpha particle does get into the Geiger tube. So the alpha particle travels into the Geiger tube, and that alpha particle will hit a gas particle in my Geiger tube, and it will ionize it, okay? And we know when things get ionized, when I have ions, that's how we can get the flow of electricity, right? The electricity is the flow of charge, the rate of flow of charge. So because I have ions, what I get then is I get a beam of current passing through my Geiger tube. Okay, so as soon as that gas gets ionized, that ion hits the Geiger tube, and that beam of current basically travels around the Geiger tube, and that's how we get a count rate of 1, right? So the count rate of 1 is because someone got ionized. Dead time means that if another alpha particle comes in here and ionizes another air particle before that current is detected, it won't also detect that other alpha particle. Okay, so it's called dead time. So just say it one more time. If an alpha particle comes in my Geiger tube and ionizes the gas, and that causes a beam of current to pass, and that's my count rate of 1. If another alpha particle comes in there and ionizes the gas before the first one has been detected properly, that second one won't be detected either. So even though 2 alpha particles, let's say I measure for a second, even though 1 second 2 alpha particles went in, because of the dead time of my Geiger tube, I might only get a count rate of 1 because it wasn't able to detect the other one in time. Okay? So just to recap, can you pop in the chat? If I'm doing an experiment to calculate the radiation given off by my nucleus, what is the problems with my results, or what could be the problems with my results? So there's my nucleus. Let's say I've got my Geiger tube, my Geiger-Müller tube. Why are my readings not always accurate? What would you write in your paper free? So just to recap it quick. So we're doing an experiment. Yeah, it's random, thank you. So first thing I write in test, you get marked straight away for just writing the word random. It's random, so maybe no decay will happen at all, nothing will be recorded, or maybe loads of decay will happen. Yeah, so because of its random nature. Yeah, good job. Sometimes background radiation is not considered, so people forget the first thing they should do is remove all radiation from the room, record the radiation in the room by itself for like an hour to figure out what the count rate of the background is. Yeah, Emma, thank you. And then what we do is we find the corrected count rate. So I have to subtract the background count rate from my actual value. Yeah, teams here, beautiful. Right, a problem is the dead time of the Geiger tube, so not all the radiation might get recorded if loads of radiation is emitted in 1 second. And beautiful J and B, right, if it's alpha radiation coming out here, a problem is it might never even reach the Geiger tube because it gets absorbed by the air particles in the room before it even gets there. Yeah, perfect, easy. Okay, so let's say these are the results from my experiment. What radiation was emitted by the source? Is it A, B, C, or D? So these are my results from the experiment. I want to know what radiation was emitted from the source. Is it A, B, C, or D? So A, B, C, or D? From the chat. So it says different materials are placed between the source and the Geiger counter. So I've got some unknown source, sometimes a nucleus in my Geiger tube. When there's nothing there, I get 1,000. When I've got paper there, I get 1,000. When I put aluminium there, it goes down to 250. When I put thick steel there, it goes down to 50. Yeah, beautiful, easy D. Nice, good job. Because clearly the one we know for sure is when there's no radiation, nothing in the present, I've got 1,000. There's nothing between my source and my Geiger counter. When I put paper there, it's still 1,000. So that means everything is able to get through that paper. So if everything can get through the paper, there's definitely not any alpha coming off that paper. And all these options had alpha in them, so that's why it had to be D with beta and gamma. Nice. Okay, so next thing now is you're asking me there, how do we know what type of decay is going to happen? So we're going to practice this now. Okay, so these are like, I really like writing decay equations. And so like conservation laws when you do particle physics, is that topic. Okay, so it says in the nucleus there are two forces. Okay, so you know there's the strong nuclear force, that's from paper 1. So the strong nuclear force, there are 4 fundamental forces: the strong nuclear force, the weak nuclear force, the electromagnetic, and the gravity force. So in the nucleus, we know there's a strong nuclear force, that's what keeps it all together. And we also know there's the electrostatic force of repulsion, right? Because in the nucleus, again, we know there's protons and the neutrons. Protons are positively charged, and if I have 2 protons in my nucleus, they'll want to get repelled from each other. So there is some electrostatic force of repulsion, but the nucleus doesn't break up because the strong nuclear force tries to bring them back together again, okay? So if this is out of balance, that's when your nucleus is unstable and it decays, okay? So the first problem might be is there might be too many neutrons, okay? So in my nucleus, there's too many neutrons, so my neutron has to decay, and the only thing a neutron can change into is a proton, okay? So let's say this is our atom and it's too neutron heavy, so it's going to decay into a proton. Makes sense? My mass number hasn't changed because a neutron changed to a proton. But my atomic number did change because we gained a proton. One of those neutrons changed into a proton. Does anyone know what is the other parts of this equation? So a neutron changed into a proton, what else gets emitted from that decay? What else gets emitted from that decay? My neutron decays into a proton. Good job. There's 2 things, if that's a hint. I need 2 things. That's your hint. Okay, so we're saying a beta particle and we're saying an electron neutrino. And someone's saying an antineutrino. So an electron, and either it's an electron neutrino or it's an electron antineutrino. What do we think? Yeah, it's a really good job. So a neutron changes to a proton. The first thing I see here is a 0 charge neutron. A proton's got a +1 charge. So the only way to keep it balanced and keep my 0 is I need to have a -1 charge. So really nice job that people figured out I need an electron. So that's going to be my beta minus decay. So it's 0 minus 1. Beta minus decay because it's an electron that comes out. And then because it's 2, the way I do it quickly is I've got 1 real particle here. I have 2 real particles here. So I need an antiparticle to balance it. So that's why it has to be an antiparticle, and really nice job, people figured out it has to be an electron neutrino. Remember, it's anti, so we draw that little line above it. And it has to be a neutrino because we want it to have 0 mass and 0 charge. Okay, nice. And then just double check, all makes sense. It's got 0 mass and 0 charge. There's 99 this side, 99 plus 0 gives me 99. 42 on this side, 43 plus minus 1 plus 0 gives me 42 on this side. So we're good. Okay. The next thing that can occur, there might be too many protons. Okay, so let's say the nucleus has got too many protons. The only thing a proton can decay into is a neutron. So let's say here I've got carbon 10, it's got 6 protons, but it's too proton heavy, so it decays into boron 10, so one of my protons changed into one of my neutrons. What gets emitted as well? So two things. If you look at the picture, I can't really give you a hint. I didn't mean to keep that in the picture. So when proton decays in neutron, what is our other two things that gets emitted? A positron and a neutrino, says Team Sarah. So Team Sarah says positron and a neutrino. Everyone says positron, neutrino. Electron, neutrino is nice. JMB, thank you. Yeah, beautiful. So what's happening is our proton decays into a neutron. I've got +1 charge on this side, 0 on this side. So clearly I need +1 on this side. The only way to get +1 is to have a positron. But if you look at it here, I've got a real particle here, a real particle here, and an antiparticle, so they technically cancel each other. So I need another real particle. So that's why it has to be a neutrino. Okay? So that's why we know that it's going to be a positron, which is beta positive decay, so beta positive decay, and my electron neutrino, or my neutrino in my electron flavor. Yeah, nice. Okay, the next thing that can occur is electron capture. Okay? So electron capture, what it means is remember when you're looking at nuclei, there's a proton in the nucleus and it captures an electron. So like say there's an orbiting electron. So you've got a nucleus, you've got your electrons orbiting it. Sometimes a proton in the nucleus could capture an electron. And when it captures one of those orbiting electrons, what two things could be emitted in that type of decay? Yeah, proton absorbs electron, good job. So what is the decay that happens here? So my proton absorbs the electron, or captures the electron. So let's say we start with carbon 11. It's got 6 protons and 5 neutrons. It captures an electron. What is the decay that happens there? Yep, good job. The proton is going to change to a neutron, right? Because the easiest way to do this is always a proton can only ever form a neutron, and a neutron can only ever form a proton, and then you figure out what the other things are after that. So if you have a proton, it has to change into a neutron, and then we've got to figure out what this other thing is. So some of us are saying electron neutrino is beautiful. Good job. Because if we look at this side, I got +1 here, I got -1 here, I got 0 here, so I need to have 0 here. The only thing I know that has 0 charge is either neutrinos or neutrons. It can't be another neutron, so that's why it had to be my neutrino. So I know I get my neutrino emitted and my neutron, okay? So what we're saying here is the top number is not changing because proton just changed to neutron. But what we've done is one of our protons changed into one of our neutrons. So the proton number, it used to be carbon 11,6, but now it's 11,5. So you don't have to do this, but you look in your periodic table to see what element's got 5 protons in it, and that's my boron. So our carbon decayed into boron because it captured an electron. Okay, this one's the easiest one. Alpha decay, do we know the numbers? What's the number A, what's the number B, and what's the number C? So an alpha decay is just when your nucleus is too big to begin with. So it's going to emit an alpha particle. So what are the numbers there that are going to be A, B, and C for alpha decay? Yeah, Sky Spark, easy, nice. Yep, nice. One more number. Oops. And one more number. Yeah, nice. So first thing I know about an alpha particle is a helium nucleus, so it's 4,2. And then again, 92 here, 90 plus 2 gives me 92. 238 here, so it has to be 234 here to give me 238. Yeah, nice. Okay, so again, what we said here is our different types of decay is that we have too many neutrons, so it's going to go, it's one of my neutrons decays to a proton. Too many protons, one of my protons decays to a neutron, or there's just too many nucleons to begin with, so I have to do alpha decay. Or there just might be too much energy in the nucleus. So the nucleus, just because it's excited, it's got too much energy, it might just give off a gamma ray. My numbers of protons and neutrons do not change, it's just called an excited nucleus, and it'll just emit a gamma ray. So that it becomes de-excited, so it has less energy overall. Okay, so can you complete the decay equation? Can you pop in the chat what's A, what's B, what's C, what's D, and what is E? So pop in the chat what's A, B, C, D, and E. A, B, C, D, and E. So it says what we're doing here is emitting a beta minus particle. So we're thinking beta minus is meaning we're emitting an electron. So it's probably the easiest number first to do C and D. And then once you do C and D, you can figure out what B is, and then you can figure out what A is, and then solve your equation to figure out what E is. So Omar says B is going to be 208. Oh, but Kai says 207. Oh, so we're debating there. Omar says C is 0. C is 0, and D is 1. D is 1. D, static spark, thank you. D is -1. Yeah, because it's not, remember the bottom number is a proton number. It can't be 1 because it's not 1 proton. It's an electron, so that's why it's -1. So D is -1. Yeah, Ishak, nice. So the top number, good job. So the top number is what Omar said, because the top number here is 208. The top number here is 0 plus something, so it has to be 208 as well. Nice. And then A, yeah, good job. A is 81. Nice. Static spark, good job, 81. So 82 plus -1 gives me 81. So 81 this side, 81 this side. Okay, nice. So what is our other particle there? What is E? I'm not sure if I saw anyone ready yet. So we're saying an antineutrino, do we agree? Yeah, good job, brilliant, right? So if we look at it here, when it's beta decay, so if I have an electron that's been emitted, that's how I would always think about it, an electron's be emitted, that's -1 on this side. So the only way to get 0 on this side is because there must be a proton here. And the only thing that can form a proton is a neutron. So my neutron decayed into my proton here, and it emitted a beta negative particle. And again, I've got one real particle here, a real particle here, and an antiparticle here. So it has to be another real particle, and it's going to be my neutrino in the electron flavor. No, sorry. I've got a real particle here. I have 2 real particles on this side, so I need to cancel it by with having an antiparticle on this side. Yeah, thank you. Sorry, you're right. It's going to be my electron antineutrino. Nice. So what happened here is my thallium was too neutron heavy. So that's why the top number stayed the same, because overall we've still got a total number of 208 nucleons, protons and neutrons, but the bottom number increased by 1 because what we changed was we changed one of those neutrons into a proton. QBLS. What is QBLS? Charge, baryon number, lepton number. Yeah, so the best way to do it, so you know how I was like, they're real and anti-real. Yeah, the best way to do it, that's just my fast way of doing it, right? Just being like, oh, there's a real particle there, there's not a real particle there. The best way to do it is you're supposed to look at charge first and say neutron is 0, proton is +1, electron is -1. So I need something with 0 charge on this side. Next thing I look at baryon number. A neutron is a baryon, so that's +1. A proton is a baryon, that's +1. An electron is not a baryon, so that's 0. So they don't want to keep it 0 this side. I needed something with a baryon number 0. And then what you were saying, the next one is the lepton number. A neutron is not a lepton, a proton is not a lepton. Electron is a lepton, so +1. So then to get 0 on this side, I needed something that is an anti-lepton. Yeah, nice, good job. So yeah, that's the way you should do it in your test. If it asks you to prove that if a reaction is conserved or not, or to prove if a reaction can be observed or not. But then just for doing these types of questions, if they come up, a nice quick way to do it is just to say, do your charges obviously first, and then you're just trying to see how many real and antiparticles you have on each side. Okay, so this was an adapted past paper question. Give a go at this one. So what it says is, a radioactive source decays by emitting alpha, beta, and gamma radiation. The student wishes to investigate whether the count rate due to the gamma radiation varies with distance from the source according to the inverse square law. So again, here's my source, here's my count rate, and they're trying to figure out if I change the distance, how does that affect the number on my count rate? So they only want to look at gamma, so how can they ensure that only gamma is detected? What would you write for 2 marks in your AQA test? How could we ensure that only gamma is detected? So it says this source is giving off alpha, it's giving off beta, and it's given off gamma, but I only want to see the results compared to gamma. Yes, JMB, good job. Well, technically you don't need the paper, right? Because if if alpha can't get free paper, it's not going to get free aluminium either, right? So yeah, so what we're going to do is you're going to put aluminium between, but that's not really 2 marks. So if you never want to just adds a bit more physics to get us 2 marks. Put the aluminium between the source and the counter. Yes, good job. That's what we want for our 2 marks there. Good job. Because aluminium will absorb the alpha and the beta, so only my gamma can pass through. Okay? Because gamma can get free aluminium. And nice, when you say about your sheet of aluminium, just always say that you want it to be thick or several millimeters thick. Right? You don't want to have like an aluminium that's a single atom sheet thick. Just be really clear that you understand that you want thick aluminium to ensure that no beta at all can get through it. Right? Yeah, nice. Okay, so she's investigating the inverse square law. So what she says now is, when the distance is 50 millimeters, she got a count rate, a number in her Geiger tube of 64. If she changes the distance to 80 millimeters, what do you predict the count rate would be? So again, this is like a paper 3 question, paper 3, section A. So what do you predict the count rate is going to be? So think about what the inverse square law is. What's that relationship? So what's the relationship with the inverse square law? So hope you're thinking, remember the inverse square law is that intensity is proportional to 1 over r squared. So remember when you have the proportionality side, you can write, nope, thank you teams here, I'm giving you hints now. So instead of having proportional, we can write intensity is equal to some constant over r squared. Oh, you've not seen that square? Yeah. So the inverse square law, actually, teams here, don't lie that you've not seen this before. Have you not been in our lessons when we did electric fields and gravitational fields? We 100% talked about the inverse square law. No? Were you there? Were you with us? Actually, to be fair, I don't think I've seen your name before, teams here, have I? 25. J&B, Emma, beautiful, yes. Nice, good job. Okay, so the inverse square law is, oh, you moved, you got Wi-Fi. Oh man, I totally get that. When you move house, the Wi-Fi takes like 2 weeks to transfer or get connected, doesn't it? I hate that so much. Yo, totally agree with you. I actually got new Wi-Fi the other day because I'm allowed to like do these lessons from home. Allowed to sounds a bit weird, but I can do these lessons from home, but my Wi-Fi is shocking. So we recently got new Wi-Fi. We were paying 25 for it was like 25 megabytes, and now we're paying £27 and we've got 1,000 megabytes. Doesn't make any sense, right? Sorry, but anyway. Okay, so what we're saying here is the count rate is going to be times r squared will equal some constant. So what I would do is 50 times by 64 squared to see what that constant is. And I got 160,000. So now we know that 64 times the distance squared gives you 160,000. So now I'm going to do 80 squared times by something must equal that same constant, 160,000. So my something, I just do the 160,000 divided by 80 squared, and we get that something to be 25 counts. Yes, J and B, beautiful. In it, yes. Yeah, beautiful. Okay, what are C and R? So the inverse square law says that intensity is inversely proportional to the square of their distance. So R is like our distance or our separation. And then what it's saying is, it was the counts that we're looking at. So what we're really saying is the counts is proportional to 1 over the distance squared. So when something's proportional, it's the thing saying the counts is equal to some constant over the distance squared. So the counts times the distance squared gives me whatever that constant was. So that's why we did our counts, which is 64, times by our distance squared to figure out what that constant was. And now I know the constant. I know that 80 squared times something has to equal that same constant. Yep, grand. Yep, fab. Right, okay, next thing then, we're just going to start a little bit of math. I'm just going to show you where the math came from. So hopefully you remember your man way back from GCSE. I can never say his name right, but I think it's Rutherford. But it's probably wrong, I don't know. Okay, so what it says is, we already knew that atoms were unstable, they emit alpha, beta, and gamma radiation. But what they did was, so remember, before Rutherford, they had the plum pudding model. So we thought the atom was a ball of mass, ball of positive charge with those negative electrons in it. They thought it was solid, right? The goat. They thought it was solid, right? They thought it was like a snooker ball. So when Rutherford came along and he fired these alpha particles at it, they expected them to hit them, right? They expected them to hit them and come back, right? Because they thought it was a solid mass. But when they did this experiment, what they actually saw was that most of the alpha particles went straight through. Most of them did. So because most of them did, they figured out actually this atom must be mostly empty. And then some of them that hit it basically came straight back at them, perfect recoil. So if that happened and our alpha particle we know was +2, to be perfectly repelled like that, it must have hit something positive because it was repelled. And that small positive thing they hit, they figured out was the nucleus, okay? So what they did was they kept firing alpha particles at it to try to figure out what is the size of this nucleus, okay? So you can see again, they have our beam of particles, most of them went straight through, and then it's going to hit this fluorescent screen, so that's how we can detect where the alpha particles hit. But then some of them like had perfect recoil, or some of them recoiled at extreme angles. And we can use that then to figure out what the size roughly of that nucleus was, okay? Things are a little bit different from year 12, or from GCSE. One thing you do need to know about is they all were emitted with the same kinetic energy, right? So all of my alpha particles from the source have the same kinetic energy, because if they were traveling at different speeds, we'd have different amounts of scattering, right? So it's not really a fair test. Fair is easy phrase, it's not really a valid test. Another thing, because remember we talked about how alpha can get absorbed by air. So like someone popped in the chat there a while ago, it's better to do these experiments in a vacuum, right? So that we ensure that none of those alpha particles are absorbed. And another thing we want is to make sure it has a really large half-life, right? Because I don't want to do this experiment just like for a minute. I want to do this experiment for a long time, keep probing it to see what's happening. So I need to make sure there's a large half-life so all my alpha particles don't just disappear and it'll affect my results. So a really large half-life. Okay, so let's say we're doing this experiment. Here's my gold nucleus. So I'm firing these alpha particles at this nucleus. 2 seconds, teams here. I'm firing these alpha particles at this nucleus. And I'm trying to figure the size of it. Okay, so clearly you can see here, what happens is my alpha particle gets fired in. As it gets closer and closer to the nucleus, it's because they're both positive, it's going to start to get repelled. So because it gets repelled, that's the path it takes. And I can't figure out actually the size of the nucleus this way. I can figure out the rough estimate of the nucleus. So if you think about it, what we're actually figuring out is the nucleus is way bigger than what it is. So it's not the best way to figure out the size of nuclei, but that's what they did, right? So can you roughly figure out what did they find R to be? What is that distance of closest approach? So I'm telling you, the nucleus has got 79 protons in it. I'm telling you my alpha particle is getting fired with 4.9 mega electron volts. Can you figure out the point S of that closest approach? Does anyone know what math we're going to do here? Yeah, to half-life, right? So remember, you know about decay. So radioactive decay has a half-life. The half-life tells us how long in time it takes the number of nuclei to drop by half. If the half-life is really short, so say the half-life is like a second, if I start out with 100 alpha particles, after a second I only have 50 left. So if I'm trying to do an experiment where I'm firing alpha particles at this unknown atom to find out what size it is, after 1 second of basically, or 2 seconds, basically most 75% of my alpha particles have disappeared. It's useless, right? It's not very helpful. So I want to have a source of radiation that's got a really long half-life, so I don't have to worry about the numbers of them dropping really quickly. So maybe a half-life of like a couple of years, right? Because I'm not going to do the experiment for years. Okay, so did anyone got numbers here, what we think to do? So again, I've got my alpha particle. It's been fired with some energy. Hopefully they're thinking anything moving has loads of kinetic energy. So something to do with kinetic energy. And then that particle is getting repelled. So think about the other topics we've done recently. What energy are we going to equate it to? So kinetic energy is 1/2 of mv squared. All of that energy is going to be basically transferred in watt, right? So it's going to, as it's approaching this nucleus, it's getting repelled. So its kinetic energy is dropping, and at point S, we're going to assume that it's got 0 kinetic energy left, right? Because you think about when you throw a ball up and it comes back down, where it changes direction, its speed is 0. So here is where our change in direction is occurring, this change in direction. So we're going to assume that its speed is 0. Yeah, good job. Thank you, electric, right? So that's the other equation there. So I'll just pop it in because you might not have your data sheet. The equation that we use when we're trying to figure out, so remember what we did was electric fields. Electric fields is a force per unit charge, or we did the electric field strength as 1 over 4 pi epsilon naught, charge 1, charge 2 over r squared. But when we're talking about energy, so remember we said that energy is going to be, the equation for energy, now it's on your data sheet, is the energy is work done, is 1 over 4 pi epsilon naught that I've given to you over here. Q1, Q2 over r. So clearly this r here is what I'm trying to figure out. What is that r where all of the kinetic energy has went into my electrostatic force of repulsion? So we're going to equate that to 1 over 4 pi epsilon naught Q1, Q2 over r. Okay, so I don't have to equate it because I know that number. I know what the kinetic energy is. It's 4.9 mega electron volts is equal to 1 over 4 pi times 8.85 times 10 to the negative 12 times Q1, Q2 over r. I'm trying to solve for r. Yeah, so r squared. So someone pop there in chat. So remember, work done is force times distance, right? So if this is our equation for force, we want to put it into an energy, so a Newton into an energy, you multiply by distance. So that's why instead of it being r squared, that's why energy is r. So this one is in your data sheet. Okay, so hopefully you're thinking the first thing is I need to get rid of these mega electron volts and put it into joules so I can actually do some math. So we want to figure out what r is. So just to give you some hints, 1.4 mega electron volts is 4.9 times 10 to the power 6 electron volts. Remember, we talked about this the other day, how to get from electron volts into joules. So I got to do 4.9 times 10 to the power 6 multiplied by 1.6 times 10 to the negative 19 to put it into joules. I know that equals 1 over 4 pi times epsilon naught, which is 8.85 times 10 to the negative 12. I have to multiply by charge 1. So remember, charge 1, which, well, there's 79 protons. So it's going to be 79 multiplied by the charge of a proton, 1.6 times 10 to the negative 19. And remember, what we're firing out of here is an alpha particle. So remember, an alpha particle is a helium nucleus, 4,2. So we know its charge is +2. So that's why we recapped what an alpha particle was, because you need to remember that. So because it's +2, we're going to multiply by 2, multiplied by 1.6 times 10 to the negative 19. And then we divide that all by whatever our r is, our distance of closest approach. So can you plug your numbers in there and see if you can figure out what r is? What is that number for the distance of closest approach? So then key steps were, you were given why did I keep writing 4.9? It says 4.8 all over the question, doesn't it? I apologize. Where did my 4.9 come from? 4.8 mega electron volts. 4.8 times 10 to the power 6 electron volts. 4.8 times 10 to the power 6 times 1.6 times 10 to the negative 19. So you're trying to rearrange your equation to find out what r is. So when I did it, I'm just making sure I use 4.8, not 4.9. When I did it, I got r to be 4.74 times 10. Did anyone get to the negative? Actually, I'll leave the negative blank. You can tell me what negative you got. So if I was doing this, negative 14, Omar. Beautiful, yes. Lovely, nice, good job. So to find r, hopefully what you're doing is 4.8 times 10 to the power 6 multiplied by 1.6 times 10 to the negative 19. Then you're going to multiply that by 4 pi epsilon naught. And then you're going to do 79 times 2 times 1.6 times 10 to the negative 19 squared divided by the number to find r. Is everyone happy? Because the things that people normally miss out is that they forget that because it's 79 protons, remember our charge of proton is +1, but that's the relative charge. So that's why it's 79 times 1.6 times 10 to the negative 19 to find what the actual charge is of that nucleus. And because an alpha particle, because it's 4,2, it tells us there's 2 protons, so it's 2 times 1.6 times 10 to the negative 19. Okay, can you give me like a plus if we're happy to try one more example then before we finish off? Or negative if we've no clue what math just happened there. Omar, Emma, Ishak, beautiful, lovely. Okay, then to finish off, we've got like 2 minutes. It's the same math, just with different numbers. Okay, so which is the correct answer here? Okay, and I'll pop up your numbers that you might need to know again, so you don't have to flip back. So remember, epsilon naught is 8.85 times 10 to the negative 12, was it? The charge of an electron is 1.6 times 10 to the negative 19. And our 2 equations is that we know the kinetic energy, and we're going to assume that all that goes into our electrostatic potential energy, and the equation for that energy is 1 over 4 pi epsilon naught Q1 Q2 over R. So basically the same math, but now what we're doing is it got the alpha particle had a different amount of energy. So what answer do you get now if we give the alpha particle a different amount of energy? So it's got slightly more energy. So hopefully we'll get a better number for the size of the nucleus, because it's got more energy. It's more kinetic energy. So again, what we're thinking here is that I've got my nucleus here. My alpha particle comes in with loads of kinetic energy. This time it was nice, they kept it 1,000 joules. Comes in, it's going to get slow down, slow down, slow down, slow down, slow down, and eventually it reaches 0 speed because of the big repulsion between that 79 charge and between our alpha particle, which is 4,2, between that +2. So I've got +2 and +79. 2.51 times 10 to the negative 15. Emma, it's not an option. So try again. I think you maybe just messed up a little bit there, math. So hopefully you're thinking 1 over 4 pi times 8.85 times 10 to the negative 12 times charge 1. Charge 1 is 79 times 1.6 times 10 to the negative 19. Because remember, it's not really +79, it's relative +79. Times charge 2 is an alpha particle, so it's 2 times 1.6 times 10 to the negative 19, because it's got 2 protons in it. Divide it by r, wherever our distance of closer approach is, and we know that that has to be equal to the kinetic energy of 9.0 times 10 to the power of negative 13. So we're trying to solve for r. So hopefully you're doing 9 times 10 to the negative 13 multiplied by 4 pi multiplied by epsilon naught. And then you're going to do 79 times 1.6 times 10 to the negative 19 squared times 2 divided by that answer to give you r. Omar says C, and C is what I got. Beautiful. Yeah, C, good job. So I got exactly 4.04 times 10 to the negative 14. Just see if you're good with that. 4.04 times 10 to the negative 14. C, happy. Good job, Jamie. Good job, Omar. Okay, so what we're thinking, are we going to join me for year 12 physics, for the year 12 physics? I'm away with it today. Are you going to join me for year 13 physics for the year? How are you feeling about year 13? I've got a few of you in here, but only a few of you are helping me out, so I really like that you guys are like popping in your answers. And hopefully you feel a bit better doing these, that you can actually pop in answers. Because I know sometimes in class, you don't want to give an answer because not only are you worried about getting it wrong, but you don't want like all your mates to think that you got it wrong. Really don't even have mates in physics. When I went to university, I wasn't friends with anyone in my physics classes. You bought the physics course. Omar, yes, you're with us. Emma, you're here next year too. Oh, happy days. Oh, that'd be good. So yeah, that's what I'm just going to talk about now. Just like talk about the course a bit. I think I did this. I think I've already talked to you about you guys, but I think I've already talked to you about it, guys. But just to let you know again, we didn't get this done, but we do this for the full course. So yeah, the full course, just so you know about it, will be basically the exact same as we're doing now. Could be 2 lessons a week with me, and the lessons will be set up the same way, but for year 13 they're longer. So do you know how we'd be doing our lessons? So we're doing 1.5 hour lessons. So we'll have more time to like sit with the math, more time to practice some exam questions. So the lessons with me will be do 1.5 lessons a week, and then you'll have the homeworks. And the homeworks just, they won't be multiple choice though. They'll be like questions and you'll answer it, and then you'll go to the video solution that I make just to make sure you got the answers right. And then the whole reason, because I'm sure you know about it, because there's a girl now, she's called Leah, so she actually works with me now. So she's just finished her exams there. She got her results the other day. She asked me one day to have a tutor, and I was like, it's mad, because I was a tutor and I'm charging like £60, but it's not fair for her to go have to pay £60 when her, like, a lot of families couldn't afford it. My family could never afford that, right? So my space is basically set up to like level the playing field a bit, right? To make it much more easier, much more accessible for people. Because it's not fair that you guys are getting charged £60 an hour for a tutor, because that's like hard on your parents to ask for that, right? And that's maybe only for one lesson a week. So the way that they're doing it for my space is they're going to offer a course for your year 13 at roughly between £800 to £1,000 depending on your course. But hopefully you guys that said you already signed up for it, you knew about the discount offer, right? It's because you're in summer school, they're giving you 40% off it, right? So they're dropping the price significantly. So you're basically paying like between 400 to 500, so like £500 for the full year. And that's, like I said, it's an hour-and-a-half lesson each time, so that's 3 hours a week with me. So 3 hours a week with me starting September the whole way up until your exams. So yeah, just make sure that you go to the YouTube, well, you're on YouTube obviously, there's that description there where you can click the WhatsApp and you just text it in so you can get that discount, right? So like 45% drop here. You get 14 days refund, but hopefully you wouldn't need it because it's me, right? And hopefully you like me already. It's not like I'm going to change significantly in a couple of weeks. But just so you know, there's other subjects too. So I know a lot of you just aren't doing physics. So there's math from Dario. Yeah, so like you can look at all his degrees there. He's mad, like PhDs, masters. Hopefully you probably all know Laura from biology. You got LaJoy and Davinder doing chemistry. And then you've got Louis who's doing a uni prep course. So like loads of options for you. So if you are interested in more than one subject, there's a thing called like an ultimate pass. And Neil. So yeah, and so Neil does do math, obviously, but Dario is the one that's going to be doing the math lessons for year 13. So he's going to be doing other math lessons for like I think he's doing year 12. Neil is doing math. I'm pretty sure it's Dario. Maybe I'm going to have to check. Maybe you guys might know better than me, but I'm pretty sure it was Dario, no? But yeah, Neil's the head of math, like. But yeah, so if you want to do the ultimate pass, it's like for all free subjects. So all free subjects are around like £1,000, 1,500. So it works out like £4 an hour. And you can pay in installments, you don't have to pay it all in one go. So just make sure that you go to that WhatsApp and click the link, right? Yes, summer school was with Neil. Yeah, so Neil's doing summer school. So like this is an example of what your lessons would look like. So really happy that I think Emma and I missed who said it a minute ago doing it with me. Emma and Omar. I'm really glad that you guys are doing it, right? So hopefully there'll be a few more ease. But my lessons will be on Tuesdays and Fridays after school. So Tuesdays is going to be, if you look at it there, we're going to start like around 5:30, and then on Fridays we're starting around 7:30. Yeah, so Neil's the head of maths, so that's why he's doing summer school. So Dario isn't in London. FYG, isn't lesson 6 meant to be tomorrow? Why is she on now? Did you just join us there now? What do you mean? Sure, we always do Tuesdays and Thursdays. We just didn't do last Thursday because of results day mind. And another great thing, like, one, the education you'll get from this is amazing, right? But another thing is the connections. So you can see Garrick's on the chat there. Like Garrick is a kid, well not a kid anymore, Garrick is a man that I used to teach. Leah and Matthew, who are currently working for us, are students from the school I just left, who are working for us as well. So there's just like so many connections you can have here as well, if you're good. But surely you would be good because you got us all teaching you, right? But yeah, it's just again because loads of people get tutors in year 13 and it just is mad expensive. So we're just trying to lay the playing field, make it more fair for people, that it's not basically just like only rich people who can afford it, and make it more accessible to more people. And yeah, it's just because I do know what it's like in school, especially if you're someone struggling. you don't want to, it's very hard to be honest with your teacher in the classroom that you're struggling, so then you try to go to them in your free time. What do you mean, Garrick? Garrick sure did the mod, who's been helping us out. But he's not really a mod. He helps me plan, sort out the lessons and stuff, and basically make sure everything runs smooth in teach floor. So yeah, I taught him like what? I can't remember. 1, 2, 3 years ago. Garrick the legend. Yeah, so he's currently in Queen's Mary, and he is like basically the second in physics right now, helped me out with everything. Him and Dario. FYG, the lesson's over, man. The lesson started at 2 o'clock. Zoya, it's a first come basis. So we're gonna offer it for all summer school. So yeah, next week when I'm talking to you again about the offer, it'll still be there, but it is a first come basis. How do you say that sentence? First come, first serve. So, but it is a 14-day refund, right? So just maybe call in. The customer service team here is amazing. Like they're so lovely, they're so helpful. So you can call in and just chat to them and see what you think about it. But yeah, so we are offering an all free summer school. So Will is still being offered next week, but it is like a first come, first serve kind of thing. Team Sarah and I were chatting. Yep. What are we doing now? FYG. Yeah, I'm just telling them about the course next year so you guys know about it more. So it'll be me. I'm just telling you guys there's the full course run next year. So this is just summer school, right? Just to get you guys a taster of what it's going to be like. And if you sadly, if you don't have joined us, then just hopefully I've helped you out. Feel a bit better about going into your year 13 year, right? You go in, you can remember some of our lessons. Or just go watch them again, I guess, if you need to. Oh, Garrick, the times changed. My bad. So it's still the same days though, isn't it? So physics still Tuesdays and Fridays. So yeah, so the times are slightly different, but I'll fix that for next week and tell you about it next week. Oh, FYG for summer school. FYG, are you GCSE? GCSE is Wednesday and Friday. This is year 13s. Year 13s Tuesday and Thursday. You're going into year 11. FYG, you're in the wrong year right now. Look at the slide at the top there. It says year 13, man. So yeah, the GCSE one is on Wednesdays and Fridays. Oh yeah, it does say Neil on that slide. Actually, Garrett, you can help us out with that. Is it Dario? Garrett, do you know? Is it actually? Maybe I can message him now to see. He's quite good at replying back really quickly. I'll put it on Slack. I'll ask him now. Sorry, mate. I made my way out. FIG, you just pop it in to say hello. Yes, I'm just messaging now to double check. Math year 13, is it Neil or Dario? So Denny's have any questions for me? I can stick around for a couple more minutes if you want to ask about the course next year, or maybe you're just like, I've had a lot of physics today, you've been informative enough, I'm good to go. So yeah, just because that's a bit off, then we'll go back just to show you about the discount. Oh, Emma, that's a good question. Yeah, so I went to uni to do astrophysics. So that's my strength. So that's why I'm teaching astrophysics. And one, because I just love it, right? But I've planned it out that if you're not doing astrophysics, it shouldn't affect you that much in the course. So the plan right now is I can't remember the month, but I'm pretty sure it's January, February. I think it's March. In March, there's 8 lessons in March, because it'll be 8 lessons every month, because it's 2 lessons a week. So in March, I'll have 8 lessons, and those 8 lessons will just be in astrophysics. If you're doing medical physics, the first 2 are useful for you also, so it's only 6 lessons that won't be useful, because lenses come up in both astrophysics and medical physics. That's the plan for right now. However, it kind of depends how the year goes. So if my timetable allows it, I might try to offer other options at the same time. So for example, like say I'm teaching astrophysics from 4 to 5 on a Friday. Maybe if the time allows it, I might see if I can also do another topic depending on them. So we'll see how many people are on the course. I can ask you guys then when you're on the course what optional topics you're all doing. And if all of you are doing basically the same one, it's not astrophysics, right? So like say for example, I don't know, say for example there's 20 people in the course next year and all 20 of you are doing medical physics and none of you are doing astrophysics. There's no point me teaching astrophysics, right? Then I will change that to medical physics. But the plan is right now, because astrophysics is one of the most popular ones, I picked that assuming that most of you are doing astrophysics. So that's the plan right now, that we will have 1 month of astrophysics. But like I said, like if we start the course in September and there's 20 of you and none of you are doing astrophysics, of course I'm not going to teach you astrophysics when none of you, it's not going to be on your exam, right? So that's all I can really help you with right now, tell you that it is astrophysics, but it's only 1 month from the whole course that we focus on astrophysics. But like I said, when we start the lesson, we'll see how many of you and what optional topics you're doing, and then we'll go from there about what's the best plan. You're doing turning points. So yeah, like I said, Emma, so like if there's 20 of you and 10 of you are doing turning points and 10 of you are doing astrophysics, I just need to make sure it works with the timetable, because there might be some clashes. So say you're not just doing physics, but you're doing physics and biology. It's quite hard to put another lesson in there if it overlaps with your biology lessons, if you know what I mean. So I know it's not really helpful to tell it to you right now, but it's right now the plan is just to do astrophysics because it's one of the most picked ones, optional topics. But when we start the course and we see who's on it and you guys tell me what your options are, then we can see what we can do from there and how to work it out to help you out the best. And I was wrong about Dario. You guys were 100% right. It is Neil doing year 13 math. So there you go. I'm sorry. I just got a reply. So Neil is doing, who was it said earlier? Yeah, we'll get those slides changed. Yeah, so Omar, you were 100% right. You're probably way gone now. But yeah, Omar was 100% right. It's Neil doing math. So sorry. Yeah, Emma, you were right too. Emma, you said it was Neil. Yep, it's Neil. I'm sorry about that slide. So yeah, just to recap, Neil is doing year 13 math. Neil, now? Neil, now? I don't know. I think Neil, isn't it? That's how you say it, Neil? Neil does math. Niall does math. Neil. Right, you're good to go. Have a lovely day. You were good to go like 16 minutes ago, so sorry if I've just droning on at you. Neil does math. Thank you, Emma. I had a little panic there that I've been saying his name wrong. But we said his name like 100 times now, so hopefully anyone watching this has got the drift that year 13 is taught by Neil. Yeah, okay, I'll see you guys on Tuesday. Have a lovely week. It's Thursday. Not that it matters because you guys are in summer holidays anyway, right? Okay, so again, really happy I'll see Emma and Omar. Hopefully I'll see a few more. See you later, Zoya, no worries.